To add, to write, I think I said in words, but yeah, you should really think of if you're making notes, maybe you want to add that subsystem relativity is really a generalization of the relativity of simultaneity. And you can also have more discussion of this. So, so what we've discussed so far in the first 5 lectures, a lot of conceptual background, technical intuition, and lots of formalism. But now, in the remaining lectures, let's try and apply this to some interesting physical scenarios. And in fact, most of what I will discuss will be basically just applications of subsystem relativity. And probably not everything, because it depends a little bit on some of the stuff I will do tomorrow. But really, what I want to get at is this notion of relational entanglement entropies, because that's a new notion of entanglement entropies in systems of H series. And so the first application, what I want to say is, again, everything that I've described so far is for quantum mechanical reference frames, as in not quantum field theoretic reference frames. So we can deparameterize unimodular groups G that are finite dimensional, so this we have kind of under control. Going to infinite dimensions, so when the group is infinite dimensional, as it is in continuum gauge theories and gravity, it's a different animal. But again, I just want to stress that so far in the general formalism, I didn't really need to say very much about the system other than it's a Hilbert space, and there's some algebra acting on it, and there's a unitary representation of G on it. That's all. That's of course pretty general. In particular, it includes also quantum fields. So if I use mechanical quantum reference frames for quantum fields, I can use this. And so this is a hybrid scenario where the quantum reference frame is quantum mechanical and the system is a quantum field. And that's the first application that we will do, and that's exactly this: observers in perturbative quantum gravity, element, and so on. So this is a sort of hybrid scenario. So QM, quantum mechanical quantum reference frame, quantum reference frames, plus Q of T system. And this is the story about observers in perturbative quantum gravity, plus these regional gravitational entropies. That has seen a lot of activity in recent years, in this whole discussion of cross products and so on. And really, what I want to convince you of is that what Witten and so on have been using in there, it's an application of the perspective mutual approach to phenomenon algebras, or equivalent to it. Of course, they didn't know that, but that's what it is. And then, another thing is that all of what I've explained is enough to do lattice gauge theories, for instance. That's another thing that I wanted to discuss, but I won't do that today. So, what is the motivation here? So, I think today I want to complete to show that this is about the perspective loop approach, what they have done, because I need to introduce a little bit of background material. So I'll talk a little bit about Q of T and regions, phenomenon algebra, some basics of this, because I don't know, maybe not everybody's familiar with this. And so one thing is that if we're in space-time, typically we want to look at some subregion in space-time, and we want to look at the causal completion of it. So we look at some causal. So we have some. This is readable. Some spatial region sigma maybe, and then U, let's say, is the domain of dependence, causal domain of dependence of that region sigma. And then, so sigma is a spatial subregion, and U is a space-time subregion. Okay, so, and then the typical problem is we want to know. Let me just write SEE for entanglement entropy or phenomenon entropy. Well, just write schematically associated with some density operator associated with that sigma. Okay. And now here, the issue in quantum field theory is a priori ill-defined. And the intuitive way in which you can interpret this, or to understand this is, I mean, if you're familiar with quantum antibody physics, for instance, then you know that, for instance, like low excited states or ground states in systems with a local Hamiltonian, and let's say there's a gap, they satisfy area laws. So that means the entanglement entropy, or the entanglement is really concentrated in the entanglement surface. So it's like, there's no long-range entanglement. You can think of quantum field theory, of course, also in some sense as a continuum limit of such lattice systems. And for, in particular, for vacuum states in QFT, okay, people have shown that they satisfy area laws in scalar field theory, and usually that was done by a lattice gauge theory, by a lattice theories, take some kind of limit. And so basically, introduce a regulator. But qualitatively, the same thing happens, that you have that the entanglement is really concentrated in the entangling surface. But when you go to the continuum, there's now all of a sudden infinitely many degrees of freedom, all the way down to all arbitrary UV scales. So there's an infinite amount of entanglement there. So it's kind of heuristically, that's how you get that the entanglement entropy a priori is going to be infinite. So so people then, I mean, as I already mentioned, typically you introduce a regulator. To do some kind of computation. The issue is, of course, that then somehow the entanglement entropies that you will have are going to be somehow inversely proportional to the regulator, and so as you set the regulator to 0, it blows up. So in that sense, when you hear about entanglement entropies in quantum field theory, in some sense, mathematically you should take that with a grain of salt, especially because when you introduce regulators, they break, of course, Lorentz invariance. So if you have or Lorentz covariance, okay? So it's usually you do a momentum cutoff or something like this. So that's in some sense it is inconsistent with some of the basic ideas underlying quantum field theory. And technically, or mathematically, really the reason is that the algebra of observables that one associates with such a region U, we call it AU, that is associated with the region is a so-called type 3 1 von Neumann algebra. And so what is interesting about this is, so it's a von Neumann algebra. And a type 3 algebra is an algebra that doesn't possess any trace. It's just mathematically not defined. When you have no trace, you have no sense in which you can define a density operator. So there's no sense in which we can define a von Neumann entropy. So that's just one way of saying that the von Neumann entropy just doesn't exist. Okay, so now comes something interesting that was noted by Chandrasekaran and Longo, Pennington, and Witten about 3 years ago. So this, I should say, this is standard quantum field theory in a curved background, so no quantum gravity there. Now, we go to perturbative quantum gravity, so we still have a background geometry that is not that is not dynamical, but now in the quantum field we include gravitons, so metric perturbations. Really, so this here is due to Bekaran et al. From 22. I will often call them CLPW, so Chandrasekhar, Mongo, Harrington, Witten. So it has become pretty famous, so that's why we may hear that somewhat more often. And now, okay, they considered several examples. Okay, there's a whole industry that came afterwards, but basically what they consider is the Zitter space. So it's a specific cosmological solution to the Einstein equations as a background, which is represented by this diagram. It's a so-called Penrose diagram. You should think of every point here in the bulk. It's S2. On the boundary, it's not. It's really this is the only place. So it's not literally a boundary, I should say. So it's in 2 + 1, it corresponds to hyperboloid. So we're this would be space. But this is a specific representation of this. And they looked at, say, region U and U prime, so causal complements of one another. These are called static patches. In the Zitter space, and the reason they are called static patches is that when you take the metric of the Zitter space and you write it for, or this is the maximum patch in which you can write it as a static metric, time-independent metric. And the reason is that it's, so the Zitter is a very symmetric solution to the Einstein equations that has isometries, so killing vector fields. And the time-like killing vector field is such that you can only extend the description. So basically, you pick as a time coordinate the coordinate along the flow of this time-like killing vector field. And the killing vector field is exactly such that you can only do this patch-wise. And so this is why it's called static patch, because in those coordinates, such a static patch looks, or the geometry looks like it's static, nothing is evolving. And now, one thing that they noted is, okay, so if I look again at such an algebra AU, so this is going to be, it's a type 3-1 algebra, so I can't actually really compute any entanglement entropy here. Another thing is that now, because we're in perturbative quantum gravity, I have diffeomorphisms as gauge symmetries, and I should impose them as well, as constraints, really. Okay? And they only looked at one single diffeomorphism. So in principle, there's infinitely many, but they only looked at a single one. And okay, what I should say, so in this case, AU now contains all the Q of T degrees of freedom that live in this region U, but it means including gravitons. So, so now includes gravitons. And so now they considered a boost Hamiltonian, or a boost killing symmetry. What that corresponds to is, so since it's, these are diffeomorphisms that this way, so it's this is essentially, it's a boost here on the so-called cosmological horizon. So why the flow lines go up in time? So this here is time, but they go up and down here. This is really what a boost does, and of course, in we do this in Minkowski space. I mean, you all know that if I do a boost. So let's say I have T, X, and then I do a boost in X direction, and afterwards I get T prime, X prime, right? So and if I look at what this does to all the description, it looks like this here.
So AU is a algebra, diffeomorphism invariant?
No, not yet. Not yet.
Oh, yeah.
Yeah.
So how do you define it?
Yeah. So that's the important question. So they don't actually say very much about it. So some of this has been clarified later, also including by work by us. But really, the way you should think about it at the end of the day. So it's not something that's completely obvious at first. You should think of this actually as the algebra of gauges. So we're in perturbative gravity. Everything inside is invariant under any matter gauge symmetry, and invariant under any linearized diffeomorphisms. Linearized, not second order diffeomorphisms. And the boost killing flow that we're going to be looking at will be a second order diffeomorphism. And okay, I don't have time to explain why that is so, but it is that it's a closed universe. And when you look at the constraints associated with killing symmetries in a closed universe, at first order they're identically zero, so they're not a constraint. So the zero order part, first order part is exactly zero, identically zero, it's not a constraint. The first non-trivial part is coming at second order. And so this has something to do also with the fact that, so they look at a boost Hamiltonian. So that is associated with this killing symmetry, and as a Hamiltonian it should be quadratic in the degrees of freedom, so it will be quadratic, for instance, particularly in the metric fluctuations. So that tells you it's a second order thing. Okay. So yeah, you should think of this here really as an algebra of all the operators in the region U that are invariant under any matter gauge symmetries and any linearized diffeomorphisms. And now they only considered a boost Hamiltonian now. So I told you already it's the second order. They didn't explain that. So that's it's been implicit in their discussion. So it's something that we explained in great detail last year. But the point is now they want to say, okay, it's a killing symmetry in isometry, and isometry is a diffeomorphism. It's a closed universe. There's no large diffeomorphism, so all diffeomorphisms are gauge. So and indeed, you can show that. Okay, there's a constraint. When you do this on a covariant phase space, there will be a constraint associated with it. So the boost Hamiltonian, let's call this H. Let's just call it H. And so this is a constraint. It's a diffeo generator. So what you want to do is we're in gravity, so we want to look at the gauge invariant subalgebra that is at least invariant under these kinds of gauge transformations. So meaning we want to also have invariance now under the second order diffeomorphisms. Yeah.
Is there no other constraint?
On what? Oh no, there's other constraints. Yes. So okay, they again don't really discuss this, but so you would, in principle, of course, you would wonder why can I look at only one second order constraint and not the infinitely many that there are? Of course, it's a field theory. Operator will have infinitely many second order constraints. Now it turns out there's this topic of so-called linearization instabilities in gravitational physics. And what that tells you is that when you look at linearized solutions, it's actually true for any gauge theory as local gauge symmetry, when you look at, as long as the dynamics is nonlinear. If you look at perturbations around the symmetric background solutions and you go only to first order, you're not guaranteed that you can extend it to higher order. What that means is you're not guaranteed that that solution is going to be consistent with a non-perturbative solution. And what I mean by that is if you look at the space of solutions, a linearized solution is basically, it should be a tangent vector to the space of exact solutions. And the point is when you look at only the linearized solutions, you're not guaranteed that this is the case. Now, you can have, therefore, unphysical solutions at first order that are inconsistent with exact solutions. And that this also only happens in closed universes, I should say. And the core example is the zeta. And now, when you go, but it now turns out this is a very non-trivial result from the 70s and 80s. is that you avoid these unphysical solutions, or the exact condition, the necessary and sufficient condition, classically I should say, for avoiding unphysical solutions is that all the charges associated with killing symmetries, that all of them are zero at second order. They're all second order constraints, so the linearization stability, the reason that these instabilities arise is that the first order part of them is exactly zero, so you're missing constraint information at first order. That's the reason why there are ultimately some solutions may be inconsistent. And basically it tells you that the first non-trivial order of the constraints for the killing symmetries, I also have to pose it on the first order theory. Okay, they're second order constraints, but I have to pose them on the first order theory. And well, there's only finitely many killing symmetries, so it's sufficient in order to avoid spurious solutions to look at all linearized diffeomorphisms and only the finitely many associated with a killing symmetry. And in this way, you can actually justify that, okay, in principle, you would have to look at the diffeomorphisms associated with the other killing symmetries, but they're all spatial. And it turns out that that these other symmetries, and that's a part that CLPW had in that paper, that if you were to implement them, it doesn't change anything about the story that unfolds. That's why you can, for qualitative purposes, ignore them. But you know, this relation to linearization and stability, so that's something we discussed in our paper, explained why that's so. It's related to linearization, instabilities, and okay, this was a paper that we wrote in November. If you want to look at this, we can read about it there. Yeah. Okay.
Sorry, maybe similar question, but is it okay to consider fixed sub-regions during the time even if you have a linearized gravity system?
Yeah, for linearized gravity, there's no problem because in linearized gravity, you just define it with respect to the background. Yeah. But you, of course, if you go to non-perturbable, you have to do something more sophisticated. Be different variant. But at linear order, it's fine. So, so anyway, so then they said, okay, you know, this boost constraint, so this corresponds to these kinds of diffeomorphisms that I have here, so they act on the regions like this and like that. Okay, they also act on this here, but it's a bit less important now. So they wanted to ask, well, what's the invariant, so the boost invariant subalgebra of this? Okay, it turns out it's trivial. So, so it's just complex numbers, C numbers. And that has something to do, okay, also with von Neumann algebras and so on, and that it's a so-called modular Hamiltonian, and the flow of this is ergodic on this algebra. So any element in the algebra basically can map to any other up to, well, not to any other, but in such a way that when you average over this, so if you were to do a group averaging, you just get C numbers.
When you're discussing this, how do you treat the bifurcation part?
Yeah, so the boost acts trivially here. So the psi, so here psi is 0.
0, where is psi?
So psi is the killing, the boost killing vector field. So psi is non-zero here, it's non-zero here, non-zero here, non-zero here, but it vanishes at the bifurcation surface.
So in library, you can consider the observable at the bifurcation point.
Yeah, but you know that's a singular point, so you don't usually associate an algebra with that.
But it's a regular point.
Yeah,
it's singular if you consider the boost Hamiltonian. But
no. But I mean, it's really, I mean, it's a codimension 2 surface, and usually in AQFT the algebras only contain smeared operators, but you space times period operators, so they will not contain this. I mean, really in QFT, the phi of x is a distribution, okay? But a distribution in a 4-dimensional sense. So I have to smear over 4 dimensions. So that's why it doesn't make sense to look at observers. So anyway, so the upshot is that if you want to look at these algebras that are boost invariant, they're trivial. So what that tells you is that there are no, in that sense, gauge invariant observers that I can associate with a region U, or also with this complement U prime. It does mean there are no gauge invariant observers in the global system. Okay? There will be non-trivial observers that are H invariant, but they will not have pure support in U or pure support in U prime. They will just be non-local. Okay. But the point is then that then you want to ask, okay, can I compute some kind of entanglement entropy for this invariant algebra? Well, it's trivial, so it's not really anything you can do. So then the way out for them was that they said, okay, let's upgrade the system and let's introduce observers. So so if U prime upgrade introduced observers. Really, what they did is so here they included a static observer here. It's called gamma. This one goes down because of that boost symmetry there. And so they have two observers, and each one of them they equipped with a clock, quantum clock. And so and then equipped with a quantum clock. In the simplest case, so they went from C basically being H, so that's still the boost Hamiltonian from here. So I would go to C equals H, and then they just used momenta. Actually, I used position variables, but it's a bit more natural to use the momenta. So in this convention, it's a bit different from how they do it, but it's equivalent. And the relative minus sign here is just because of the boost symmetry that goes forward in time here and backward in time there. Okay. And so this is now the new Hamiltonian constraint that they impose on the combined system. And then, so what you do is that you go now from this algebra, which is trivial.
Excuse me.
Yeah.
Is it important to introduce two observers?
Yes. So to make this whole thing, well, depends on what you mean important. You can in principle do it with one, but it turns out that it is convenient to introduce two. But the reason of which is maybe I'll explain that later. But it's basically you're gonna get von Neumann algebras, and if you only introduce one, and then you represent the von Neumann algebra you're interested in on the physical Hilbert space, on the perspective neutral Hilbert space, it's no longer a von Neumann algebra.
No.
So,
Von Neumann.
sorry?
Sorry, could you say?
Von Neumann algebra?
You mean not?
Yeah, so and if you have only a single one, then you look at the dressed observables with respect to that observer, it turns out to be von Neumann algebra kinematically. But if you want to represent that on the physical Hilbert space, it no longer is a von Neumann algebra. And then the kinds of arguments that are important don't apply then. So
Is it because the AU is not convergent as the AU prime?
yeah, it's related to that. So anyway, so what they go to is then AU tensor, and then the two reference frames. And here, in the simplest case, okay, it's just momenta. So they will come with an L2 over R. And we're only looking at U plus one single observer. We're not looking at the second one here. And then you look at the invariance under the C. So we have an upgraded system. And this turns out to be non-trivial. And this is so-called cross-product algebra. And maybe I already tell you what it is. And I wanted to introduce some background on what algebra is first before I tell you what it is. But by angle brackets, I now mean algebra generated by whatever I put inside. It's e to the I t1 hat h, yeah, so it's this h here, a to the minus I 1 h to the I s p1. And then I allow A to be in AU, and S and R. I put a double commutant on this because of this is a phenomenon algebra. I will explain why. But maybe you can recognize what this is now. So, I've shown you all the ingredients already in this course. Does anybody recognize the first part here? Relational observables describing now the system, which is AU, so the Q of t degrees of freedom relative to this ideal quantum reference frame. Remember, I actually wrote down once relational observables for a clock, for an ideal clock. And the reason I spelled it out is because it exactly is this.
So why there? So what observer has an ideal clock?
Yeah, later. So afterwards, you can project this to non-ideal clocks. That's what they do also. But the point is the cross product is defined in terms of ideal reference frames. So these are relational observables relative to an ideal clock. And what's that here? It's the reorientations of the clock. So the statement is what you get here is it is the phenomena algebra generated by the relational observables describing the Q of t degrees of freedom with respect to the clock inside that region plus the reorientations of that clock. So and this is the so-called cross product. Okay, maybe I should. This is AU, technically written in this following way. So it's a so-called cross product. So you're crossing this phenomenon algebra AU with a group action. In this case, it's the translation group, and it's the translation group that's generated really by this constraint here. Okay, it turns out that this cross product is given by this. Okay? It's one representation of it. And so this is in fact a general insight that cross products are Neumann algebras generated by relational observables and reorientations for ideal quantum reference frames. So here it's just for clock reference frames. So the reason why people are really interested in this is that this AU is a so-called type 3-1 algebra. There's no, doesn't have any traces, so it doesn't admit any notion of entanglement entropy. But the cross product is a so-called type 2 infinity algebra, which actually has traces, and you can define density operators on it. not every element in the algebra is trace class, but you have a trace, and you can use it to define density operators, and so you can actually compute entanglement entropes now. So they didn't actually use any language of quantum reference frames. They just talked about observers and so on, and cross products and so on. But it should be clear from what I've already discussed that what I'm telling you here, I mean, there's nothing else in quantum reference frames. These quantum clocks, they're quantum reference frames, and this cross product algebra is just a fundamental algebra generated by the relational observables relative to that clock and reorientations.
Excuse me.
Yeah.
So it is trivial that combining a quantum clock to that system reduce the type 3 to type 1.
Yeah, so I will try to explain that a bit later, why that is so. From what I've told you, it's not obvious at all. So it's, I mean, you need to know a little bit about details of fundamental algebras. And
so in that sense, and as a non-trivial result, and it succeeded in becoming to the type 2.
Yeah, it's not trivial.
I see.
I mean, so I'm just telling you this. So this is in some sense the motivation for what comes now. I want to explain that in a little bit more detail, but now you know where we're going to go. Okay. So that this is a type 2 algebra. If you don't know about fundamental algebras, it will not be obvious to you at all. But the crux is, it is a type 2 algebra, so all of a sudden you can compute entanglement entropies. And so what that tells you is basically in quantum gravity, because sometimes you can view this here as having just AU, and you don't go to a relational description of these regional algebras. There's not really any sense in which you can compute entropies. But if you go to a relational description of the Q of t degrees of freedom, it intrinsically regularizes your algebra in such a way that you can compute entropies. So that's really a remarkable insight that basically a QRF description of regional Q of t degrees of freedom, it's important that gravity is involved. So this time transition has to do with gravitational properties. But that this relational description is an augmented description, I mean, as I made clear, that this actually leads to well-defined entropies.
So in this discussion of gravity, it seems that gravity doesn't play an essential role.
Oh, it does, because gravity is the reason why you impose this constraint.
But even QFT without gravity, you can always consider quantum reference frame and then you can impose.
Yeah, but if you're in QFT in the Zitter space, without gravity, you will not consider the killing symmetries as a gauge symmetry. Because it's a physical symmetry in that case. So if you write this out in the covariant phase space, it will not be a degenerate direction in your phase space of the symplectic structure. But in gravity it is. So that's really the core reason why it relies on gravity. It's really crucial that it's about gravity.
So you mean the dynamical gravity is not important?
Well, dynamic gravity is important because the reason that we impose constraints is because gravity is dynamic. Right? Because I'm including gravity. So what I would do is, I take my QFT action, I take the gravitational action, I write it in terms of metric fluctuations. But I have metric fluctuations, and because of the metric fluctuations, I have, at the end of the day, I'm talking about diff invariance here. And that diff invariance, these are gauge symmetries of that action. But that's not true when I only have matter.
But you have matter QFT, and if we gauge the killing symmetry.
But you wouldn't gauge it because it's not a gauge symmetry in that case. So the killing symmetries are only a gauge symmetry.
We can always gauge any global symmetry.
Well, a global symmetry in general is not a gauge symmetry, right?
Yeah, but we can gauge them. We can gauge.
But you have no reason to do so.
Yeah, of course.
Because it's not a gauge symmetry, so you don't impose a constraint.
If you gauge it, I think it's.
I mean gauge is.
But yeah, I mean, anyway, the summary is really, I mean, you can do covariant phase space analysis and so on, and so it's really crucial that you're in gravity. The metric is dynamical, metric fluctuations, but that's the reason why you get these constraints that you have to impose. Without gravity, you don't have it.
I didn't mean robust method to robust method, but I didn't to just impose or select or use invariant sector of the robust method.
So I mean, okay, yeah, I mean, I still think the best way to see it is really in terms of covariant phase space analysis, and you can do this with, say, scalar field theory in the zeta space. Look at the syntactic structure, you will see it's not, killing symmetries are not degenerate directions, so it's not a Gibbs symmetry.
So, and then one question, is it important to consider ideal clock or?
Yeah, so it turns out that this notion of cross products is always involving ideal quantum reference frames. But yeah, you can afterwards, so this is the easy entry point. You can look at bounded Hamiltonians for the clock also, and that turns out to give you projections to subalgebras of this. They actually have, depending on if the clocks are bounded from below, these subalgebras are even nicer than this one. There are so-called type 2-1 algebras, which are such that all operators are trace class. The identity can be normalized, so they're even nicer.
So it's important to get a type 2-1 algebra.
No, I mean, this here is a so-called, I mean, okay, maybe I want to explain it a bit later, but this is a type 2 infinity algebra, which means not every operator is trace class. In particular, the identity is not normalizable. And, which has a slight disadvantage in the sense that entanglement entropies or phenomena entropies are only defined for differences of states. Okay, and so only entropy differences are well defined. Entropies are otherwise only defined up to an additive constant. Okay? And this constant you can fix by differences, so state independent constant. But if you go to type 2-1 algebras, then you have then you can fix unique. Once you normalize the identity to have trace 1, which you can do, then everything is fixed.
I was confused because we didn't at all argue the ADS case. The P's are not P is not bounded from below, so.
Yeah, so that's because it's an ADM Hamiltonian in that case, and I mean it's also in the Schwarzschild case.
But even in that case, they had a cross product and type 2 algebra.
Yeah, but type 2 infinity in that case.
Yeah. So.
But anyway, I think I need to introduce a little bit more to. So this was kind of giving you a picture of where we want to go. So this goes into some details that maybe will become clearer later on. So. So it's just to motivate you to stay tuned somehow. So yeah, I guess I should probably add. So this is a type 2 infinity algebra. So that means it has trace and. Put a delta SE here for the reason that I mentioned, that it's differences of entropies that I want to find. So, I mean, I said these things, I just wanted to note them down in case you take notes. So, I have to think a little bit because we have 15 minutes left. So I'm going to give you a crash course on some basics of phenomenon algebra to understand this better. Maybe it is relevant to understand the intuition for why this is a type 2 algebra, but for this I need to do a bit more. So this one. So typically in quantum theory, we're interested in unital star algebras. So what that means is, so they're closed under addition, multiplication, and unital star algebra under dagger relations, and they contain the identity. So unital means it contains the identity. Star means it's closed under a dagger relation. So, okay, why do we want algebras? Okay, that's, you know, whatever we do in terms of observables should be closed. We want the identity to represent doing nothing on the system. And it's also natural to look at star algebras because it should be closed under Grecian creation. Now we're going to impose two more conditions on this, and that will be a von Neumann algebra. So, so we want to restrict further that some algebra of bounded operators so this is a we say some subalgebra of bounded operators. So this is by B of H, we mean the bounded operators on some Hilbert space. And we want to restrict that whatever an observer or an agent has access to is supposed to be bounded. And I mean, that makes sense. That there's no new experiment, no divergencies that you're creating and so on. And the reason bounded operators are nice because they have a common domain and you can multiply them and they form an algebra. So unbounded operators don't usually form an algebra. And then now comes the next thing is we want to look at a particular closure. So here I'm not talking about the closure in that sense, but you can now think of the algebra. So some unital star algebra of bounded operators, and we want to close it in an additional sense in terms of limits. Okay. You can think of it as closing it as a topological set. And here, okay, let me actually directly say what it is. It's a so-called weak closure. But it has a physical interpretation. So, you know, so what does it actually mean to measure operators? So in practice, you would, you know, measure some observable up to a certain accuracy, so certain coarse grading, but in some sense you can view this as taking, as you know, basically measuring matrix elements of operators or of a sequence of operators. Maybe the sequence is given by making the operator more and more fine-grained. So the resolution of the experiment is going to be more and more fine-grained. So matrix elements of a sequence of operators, say A1, AN, and then we somehow measure phi AI psi. Now, principally, we could say for all well, when you measure, you will do that for maybe not all states. Okay, why not for all states? All psi, phi, and h. And now you could imagine that you have a sequence such that that I take the limit I going to infinity of the sequence, that this converges to some phi a psi. So some operator A evaluated in certain states on your Hilbert space. I suppose it's true for all Hilbert space elements. Then experimentally, it would mean basically, at some point when I is big enough, the resolution is fine-grained enough, you can't really distinguish what you have measured from this operator A. So in some sense, you can say for all practical purposes, you have realized in your measurement this operator A. And so it is in that sense kind of reasonable to include that operator A in your algebra. So again, you can think of the sequence of operators as being with a finite resolution. So FAPP means for all practical purposes. So AI, so it's used in the quantum foundations community often. But AI indistinguishable from. So you could say the experimenter has realized A. So it's natural to include A in the algebra. So it's kind of an operational motivation for why you would want to consider that.
Can I make a really pedantic mathematical point?
Yeah.
I'm pretty sure it should be a net rather than a sequence.
It should be what?
A net rather than a sequence.
Okay.
I
okay. I mean, yeah, but I think I think you're right. But a net of operators, which is it's a generalization of a sequence. But if you don't know this, then the sequence is fine. Think about this. And so, and an algebra closed in the sense. Well, is weakly closed. And so this here is a definition of phenomenal algebra.
So before you said if we include only just a single observer, we get something not phenomenal.
Well, I mean, so if I don't want to go into these details now. It's really a bit distracting and besides the point. But if I don't include this observer here, this cross-product algebra will still be phenomenal algebra.
Oh,
Yeah. But the point is, the way I've defined it, I haven't defined it on the physical Hilbert space yet. It's a I have not defined it on the physical Hilbert space yet. This is still a kinematical definition of a Gaussian algebra. What we're going to be interested in is take that algebra and represent it on the physical Hilbert space. And if I don't include that observer, this will no longer be a phenomenal algebra on the physical Hilbert space. By the way, one thing, if you want to read more about phenomenal algebras, a good reference is this Haag book called Local Quantum Physics. So it's probably the most famous entry point to the mathematical foundations of quantum field theory. And then actually a lot of the stuff is, for instance, also this really nice review article by Edward Witten on QFT and on entanglement and QFT. This is Witten, Prof. His article from 2000. 19, 18 or something. I don't know. So you can read more about these things. So
I have still so Hamiltonian is not bounded, so it is not included in this one.
Okay, so this the clock Hamiltonian, yeah, I mean, at the moment this is general phenomenon algebra, so we have to work ourselves forward. But that's true. So you're right that P1 is not contained in the bounded operators on this Hilbert space, but you can take any bounded functions of it. So, okay, maybe we're pointing at that definition here. So if you remember, okay, so I wiped it out, but in the cross product, I wrote e to the I s P1, that's a bounded function of P1. Okay, time is basically up. So now we want to have basically von Neumann algebras and Q of T. So, yeah, let's pick the picture of the Zitter space again. It's kind of convenient. U and U prime are causal complements. Okay, so here the statement is then, I guess it's in some sense folklore, but then you can ask Christie and he will tell you exactly the precise mathematical assumptions that go to the proofs of this, that that in quantum field theory, in the algebraic formulation, that the algebras of local operators associated with regions are von Neumann factors. So regional Q of T algebras are von Neumann. And maybe what do we actually mean by regional Q of T algebras? What is contained in them? Well, you take any smeared operators of your basic quantum field, and you take bounded functions of those. And then, you also look at the time evolution of them. So you can look at, for instance, algebras associated with that are in some sense simple on a time slice, but you can also look. You also want to take the time evolved operators. So at the end of the day, we'll take any bounded operators that you can construct out of the local spheres of the. Okay. So it's really bounded operators of regional spheres. Actually, I forgot one thing that we want to get to now is. So this is a definition of von Neumann algebra. It's somewhat convenient to talk about this weak closure in terms of what the operational meaning of this is. But I find, at least technically, often an even nicer way to think about it is that there's this von Neumann theorem that von Neumann algebras can also be characterized in another way, namely by being equal to their double commutant. So. So A is von Neumann, basically, then you have that A double prime is equal to A, and or A prime, so this is the commutant. So this is the set of A, it's called A prime, in the set of bounded operators on your Hilbert space, such that A prime, let me just write it like this, that this is 0. And A double prime means you take the commutant of the commutant. So clearly, if I take the commutant, then A is going to be the commutant of the commutant. That's always going to be true. But that it's equal to the commutant of the commutant, that's a non-trivial relation. And this von Neumann theorem tells you that weak closure, this definition here of you need to have all these features here, that is equivalent to the algebra being closed under bicommutation. So you can replace this weak notion of closure by this bicommutant notion of closure. So, and this is convenient in quantum field theory because we have causality in quantum field theory. So AU prime is causally disconnected from A. So of course, we have causality. So we'll have that AU, and AU prime, that this is going to be 0. So that tells you that AU prime is contained in the commutant of AU. And now, it is a postulate in the algebraic formulation of quantum field theory that it's not only contained in it, but is equal to it. And this goes in the name of Haack duality. It's an axiom, an AQ of T is Haack duality. Which is to say that that AU prime is equal to AU prime. So it's apparently quite generically true in the cases that people have under control. There are some counterexamples to this, but they're somewhat exotic. So this appears to be a good definition. And so, in that sense, really, if you think about this, there's a very nice relationship between the von Neumann structure and the causal structure of spacetime. So, in the sense that, in causal relations, you also put sometimes a prime, like here. You say, oh, that's the complement of this causal relation. And the point is that the causal primes are consistent with the algebra primes. And now, again over time, let me maybe still define what a factor is. So a factor is really a generalization of a subsystem partition. So, so a factor is if you have A intersected with its commutant, so for von Neumann algebras, as equal to C numbers. So that means I have an algebra, and the only thing it shares with its commutant is C numbers. That means in particular that the only elements inside the algebra A that commutes with everything else inside that algebra is just the identity component. So you can think of this really as a generalization of A1 or A prime in quantum mechanics. And so quantum mechanics is of course true. I mean, if I have two Hilbert spaces, and so maybe I have H tensor H prime, two Hilbert spaces, I have a tensor product, and then suppose A and A prime are just the set of bounded operators on this Hilbert space and that Hilbert space. Of course, I can look at this here and they will satisfy that. But the point is that this is really, it is a generalization because it also holds when you cannot write a tensor product. So also in the Hilbert space, and in particular in quantum field theory, that's going to be the case that if I take the Hilbert space associated with a global Cauchy slice, you cannot write it as a tensor product of something, a Hilbert space here and a Hilbert space there. And that's because, again, of this UV structure, that there's infinitely many degrees of freedom. It's not a lattice. You cannot just cut it. But this will still apply in that case. So that's why that really is a, when you talk about factor algebra, and that's really can think of that as a definition of a subsystem in a really general quantum field theory context. And now I realize that I'm already beyond time. So maybe I'm going to end here, and I'll try to explain a little bit more about this von Neumann structure tomorrow to give you some intuition why these cross products, why there's a type conversion. And then I'll tell you also why the entanglement entropies that you compute in this way, these why they're relational entropies in the sense in which I've kind of hinted at in the previous lecture, and why subsystem relativity will imply that these gravitational entropies will actually be quantum reference frame independent. So are there any questions at this point?
I'm sorry, I don't understand the logic about the factor, and it is just a definition of the factor, or
Sorry. I mean,
I'm sorry.
So yeah, A is a factor if this is true. Sorry.
I see. So in our case, in the picture, in the figure, and the condition is satisfied for
QFT algebras.
Yeah.
Yeah.
Because
Okay. So I mean that's so there are in particular also these type 3 factors usually under general conditions. I mean, okay, I don't think a particularly. I don't know if Christie has a particularly good intuition behind it.
So there are mild analytic conditions which are slight strengthening. So this nuclearity property is something that you need in order to be able to define tensor products properly on infinite dimensional Hilbert spaces. But it's what they call nuclearity is slightly stronger than what the functional analysis normally call nuclearity. So there is no nice projection.
Yeah, so I don't think there's, like a nice physical intuition.
Yeah.
I don't know.
Any simple example?
So nuclearity is fairly natural. It sounds horrible when you look at the mathematical definitions, but the nuclearity condition, which is always imposed on your Hilbert spaces, basically means that everything is almost approximated by finite dimension, by a finite dimensional projection. So it's like all the information can be obtained by going to a finite dimensional projection. So that's what nuclearity means. So you can describe a quantum field by looking at discretization. It's possible to take a lattice discretization and then
But then, because it's with von Neumann algebras, it's really a lot about limits, and these limits are not particularly intuitive often.
Can you give an example non-factor algebra?
So I don't know off the top of my head, but the point is all von Neumann algebras decompose as a direct sum, possibly or direct sum of factors. So these are kind of the structural, structure.
For gauge theory, it's not
No, for gauge theory, that's also true.
but we can have
But for gauge invariant operators,
but we can have some non-trivial centers.
oh, okay, yeah, but that's so. Here we're only talking about if this was a gauge theory, you would only take gauge invariant observables that have pure support inside. Yeah, it's true. You can have like electric Zeta algebras and so, but then you have to add basically the normal electric field on the corner. But yeah, you're adding something to it.
Any more questions? So if not, then let's thank Philipp for today.